Welcome to the Learning Assistant app YouTube channel. Today, we are going to dive into one of the most beautiful and, frankly, most misunderstood concepts in all of chemistry, resonance, also known as the mesomeric effect.
If you've ever looked at a chemical structure on a page and felt like it didn't quite tell the whole story, you're right. In fact, for many of the molecules that make life possible, the standard way we draw bonds is essentially a lie. To understand why, we need to move past static drawings and see molecules for what they truly are: dynamic, shifting clouds of electronic probability.
To start, let's look at a mystery that puzzled chemists for decades. This is benzene, C6H6. If we draw it using our traditional Lewis structure rules, we see a hexagon of carbons with alternating single and double bonds. Think about what that implies. In chemistry, a single bond is like a long, somewhat flexible rope, and a double bond is like a shorter, stronger, tighter spring. If benzene actually looked like this drawing, the molecule would be a lopsided hexagon. Longer sides where the single bonds are, and shorter sides where the double bonds are. It would be an irregular shape. But when we measure benzene in a lab using X-ray crystallography, something strange happens. We find that the molecule is a perfect, symmetrical hexagon. Every single bond is exactly the same length. They aren't as long as single bonds, and they aren't as short as double bonds. They are somewhere in the middle, exactly 1.5 bonds long. How can you have half a bond? This is where the mesomeric effect comes in. It is the universe's way of saying that electrons aren't always stuck between two specific atoms. Before we look at the math and the arrows, let's build a mental model. Imagine I show you a picture of a mule. A mule is the offspring of a horse and a donkey. Now, if I try to describe a mule to someone who has never seen one, I could say, on Monday, Wednesday, and Friday, it's a horse. On Tuesday, Thursday, and Saturday, it's a donkey. This is what we call resonance structures. I draw one version, the horse, and another version, the donkey, because my language lacks a single word for mule.
But here is the crucial point. The mule isn't flipping back and forth between being a horse and a donkey. It doesn't spend 50% of its time as one and 50% as the other. It is always a mule. The mule is a hybrid. It is a single, stable animal that has characteristics of both parents simultaneously. In chemistry, the resonance hybrids are the mules. The structures we draw with curly arrows are just the horse and the donkey. They are limit cases, theoretical drawings we use because our pens and paper are too primitive to draw the reality of delocalized electrons. To understand why this happens, we have to look at the orbitals. Let's zoom in to a carbon-carbon double bond. Every carbon in a double bond is sp2 hybridized. It has 3 orbitals pointing out in a flat plane, the sigma bonds, and 1 p orbital sticking straight up and down, perpendicular to that plane. When 2 p orbitals overlap side by side, they form a pi bond. In a normal, isolated double bond, those electrons are trapped, localized between those 2 carbons. But what if we have a chain where every carbon has a p orbital? Imagine a line of people holding umbrellas. If 2 people hold one umbrella, they are bonded. But if a whole row of people are all holding umbrellas that touch each other, you don't just have individual pairs. You have a continuous canopy of silk overhead. This canopy is the delocalized pi system. The electrons are no longer owned by 2 atoms. They are free to roam across the entire system. This movement of electrons through the pi system is the mesomeric effect, M effect. Now, let's look at how we actually represent this on paper. We use curly arrows to show the movement of electron pairs. There are 2 main flavors of the mesomeric effect, plus M and minus M. Think of M as electron giving.
Some groups of atoms have a lone pair of electrons, like the oxygen in an OH group or the nitrogen in an NH2 group. When these are attached to a conjugated system, they don't hold on to those electrons tightly. They push them into the ring or the chain. Watch the lone pair on the nitrogen. It drops down to form a double bond with the neighboring carbon. But carbon can only have 4 bonds. So the existing pi bond next to it has to break and jump onto the next carbon as a lone pair. This creates a chain reaction of shifting charge. This is the plus M effect. On the flip side, we have the M effect, or electron withdrawing. This happens with groups like nitro, NO2, or cyano, CN. These groups act like electronic vacuums. They pull electron density away from the chain or ring toward themselves. Notice how the arrows move now. They point away from the benzene ring and toward the nitro group. This makes the ring electron poor. At this point, you might ask, wait, isn't this just the inductive effect? This is a common misconception. Let's clarify. The inductive effect, I effect, is about electrons shifting through sigma bonds, the single bonds, due to electronegativity. It's like a tug-of-war through a rope. It gets weaker very quickly as you move away from the source. The mesomeric effect, M effect, happens through the pi system. It is much more powerful and can transmit an electronic influence across a very long molecule without losing strength, as long as the canopy of p orbitals is intact. To draw valid resonance structures, we have to follow some strict cosmic rules. 1. You can only move pi electrons or lone pairs. You never break a single sigma bond. If you break a single bond, you aren't doing resonance, you're doing a chemical reaction. 2. The nuclei of the atoms must never move. If you move an atom, it's an isomer, not a resonance structure. 3. The total charge of the molecule must remain the same in every drawing. The acetate ion. The negative charge sits on one oxygen, which is single bonded to a carbon, while the other oxygen is double bonded. But why should one oxygen be different from the other? In reality, the negative charge is shared equally between both oxygens. By drawing the resonance structures and showing the arrow flipping from one oxygen to the other, we demonstrate that the real molecule is a hybrid where each carbon-oxygen bond is actually a 1.5 bond. Why does the universe love resonance? In one word, stability. Imagine you have a heavy backpack. If you carry it on one shoulder, it's painful and unstable. If you spread the weight across both shoulders and use a waist strap, it becomes much easier to carry. Electrons are the same. Charge is heavy. If a negative charge is stuck on one single atom, that atom is stressed and reactive. But if that charge can spread out, or delocalize, across 3 or 4 atoms via the mesomeric effect, the energy of the molecule drops. The molecule becomes much more stable.